Welcome to Alphanumeric Tricks. In this video, we are going to see how to get the solution of the problems under the type first order nonlinear partial differential equations. The type of the problem is type 3, case 3, f of z pq is equal to 0. And last video also we have seen that how to get the solution of f of z pq is equal to 0 type of problem. That is same type of problem. This is a continuation of the previous video. That previous video link is available in the description box. If you want to, please have a look on it. Now we are going to see how to get the solution of these two problems one by one. First we will see how to get the solution of z squared is equal to 1 plus p squared plus q squared. Take the given problem as equation 1. Here the remaining two problems are in the previous video. And now we have to identify the type of the problem. Here z, p, q alone is present. So this is of the type 3, case 3. That is f of z, p, q is equal to 0 type of problem. And here what is the procedure for finding complete integral? We have to substitute q is equal to ap in the given problem. After that we have to find out the value of p, and that value of p and q is substituted in the dz is equal to pdx plus q dy, and integrating we can get the complete integral. Singular and general integral are similar to that of type 1, type 2 problems. Okay, all the type 1, type 2, type 3 and type 4, all the type of problems, general and singular integral are same procedure. Complete integral differs from different types. Now, what is that is how will you find out case 1 type of problems for complete integral? Just we recollect it. That is, we have to substitute q is equal to a, and that is substituted in the given problem, and find the value of p. That values of p and q are substituted in dz is equal to pdx plus q dy, and integrating we can get the answer. In the same way, the substitution for case 2 is we have to substitute p is equal to a. The same procedure we have to follow. Now we will see how to get the solution of this problem. First we have to find out the complete integral. Before going to find out complete integral, we have to write the problem is of which type. So this is of the form f of z comma p comma q is equal to 0. And now we have to make use of the substitution q is equal to ap in the given problem. Then the problem becomes z squared is equal to 1 plus p squared plus a squared p squared. Now we have to find out the value of p. So we have to take z1 to left hand side, it becomes minus 1. So z squared minus 1 is equal to, here p squared is common, take it outside, p squared into 1 plus a squared. Now we have to take that 1 plus a squared also to other side denominator. Then p squared is equal to z squared minus 1 divided by 1 plus a squared. When you're taking square root, we get the value of p, which is equal to root of z squared minus 1 divided by root of 1 plus a squared. Now we have to substitute this value of p and q in dz is equal to pdx plus q dy. Then we have, that is dz is equal to pdx plus the value of q is equal to ap into dy. Now we have to integrate this. We have integral dz is equal to, p is common, take it outside, p into integral dx plus a dy is under integral sign plus a constant. Now we have to substitute the value for p, that is p is equal to root of z square minus 1 by 1 plus a root of 1 plus a square, and remaining terms are as it is. Now we have to take, because z is, that is this z square minus 1 is function of z, so we have to take that to be the left hand side. Then only integration becomes easy, that is we can easily integrate it, because left hand side you have dz is there, and along with the root of z square minus 1 we have to take that 1 plus root of 1 plus a square also. Just for the convenience we are taking that, that's all. Okay, now we taking that to other side, it becomes, that is when you taking root of z square minus 1 by root of 1 plus a square to other side, it becomes reciprocal, that is root of 1 plus a square divided by root of z square minus 1. Now we have the term like this, root of 1 plus a square into integral dz by root of z square minus 1 is equal to integral dx plus a dy plus a constant of integration. And now this is root of 1 plus a squared is constant, right as it is, and integral of dz by root of z squared minus 1 is log of z plus root of z squared minus 1. This is the standard integral formula, you should remember. is equal to integral dx is x plus a into dy is integral dy is y plus this constant is c. This is the required complete integral for the given problem. Number that is equation 2. Now we have to find out the singular integral for this. A singular integral is obtained by differentiating the complete integral partially with respect to the available arbitrary constant. Here the constants are a and c. So you have to differentiate this with respect to a and c, and you have to use the rule dou z by dou a is equal to 0 and dou z by dou z is equal to 0 because a and c are the constants available. Using that, we have to eliminate the arbitrary constants a and b. We can get the singular integral. But here, one thing you should remember, before going to differentiate this, you should check the constants, arbitrary constants in the complete integral. If any one of the constant is separately there, first you have to differentiate that equation with respect to that constant, because we can easily conclude that answer. Okay. Otherwise, you have a lengthy differentiation. To avoid that, we have to differentiate. That is the easy way we can get the singular integral if any one of the arbitrary constant is present in separately. Now c is present separately, there c is separately in our equation, so we have to differentiate this with respect to c. First, so the differentiation of dou z by, that is, this is differentiated with respect to c. So dou z by dou z, which is equal to 0. Thus using this, it becomes 0 is equal to x differentiation with respect to c is 0 because x is constant when you're differentiating with respect to c. Similarly for ay, which is also 0. Plus differentiation of c with respect to c is 1. So 0 is equal to 1, which is an impossible result. We got it. That's why we conclude that there is no singular integral for the given problem. Okay, this is that. That's why I say that previously I told that just first differentiate the constant which is separately there in your complete integral. For that reason only I told like this. Okay. Now we have to find out the general integral. What is the rule for finding general integral? You have to reduce two arbitrary constant in the complete integral to single arbitrary constant with the help of the substitution c is equal to phi of a, that is obtained by one constant in the complete integral should be written as the function of the other constant, that is substituted in the complete integral. We, instead of c is equal to phi of a, we can take a is equal to phi of c. Also substituting that in the given equation 2, we get root of 1 plus a square into log of z plus root of z square minus 1 plus x plus ay plus c is replaced by phi of a. Number that equation as 3. Now we have only single arbitrary constant is there. You have to differentiate this equation 3 partially with respect to a. Then you have this term is differentiated with respect to a first. So root x formula you have to apply. Root what is differentiation of x power n into x power n minus 1. How will you write root x power half? So differentiation of x power half is half into x power half minus 1. The same rule is applied for this d by dA of root of 1 plus a square. That is root 1 plus a square whole power half, we can write it. That can be written as half into 1 plus a square power half minus 1 into differentiation of 1 plus a square with respect to a is 2a, because this becomes 0. 1 differentiation with respect to a is 0 and a square differentiation with respect to a is 2a. This 2 get cancelled and half minus 1 is minus half, that is 1 plus a square whole power minus half is taken to the denominator. It becomes plus half and it is root. So a by root of 1 plus a square, which is the differentiation of root of 1 plus a square. So substituting this into this log of z plus root of z square minus 1 is constant because there is no a term present, is equal to, this becomes 0. Differentiation of x with respect to a is 0 plus y is constant, right as it is. Differentiation of a with respect to a is 1 plus phi of a differentiation with respect to a is phi dashed of a. Number that equation as 4. Now using 3 and 4, we have to eliminate the arbitrary constant a. We can get the general integral. Further, the simplification is not possible because phi of a is not known to us. That's why we conclude our result like this. Eliminating a between 3 and 4, we can get the general integral. Okay, that's all the solution of this problem. Now we will see how to get the solution of the another problem. P into 1 plus q square is equal to q into z minus 1. Here also the problem is of the type, number the equation is 1 and the problem is of the type f of z comma p comma q is equal to 0 because z p q alone is present in our problem. Now we have to find out the solution for this. First we have to write the complete integral. The procedure is similar to that of the previous problem. Only thing is the equation is different. That's it. Okay, now this is of the form f of z comma p comma q is equal to 0. Now we have to substitute q is equal to ap in the equation. That's the given equation 1. Then your problem becomes p into 1 plus a square p squared is equal to ap into z minus 1. Okay, and don't cancel off this p here itself because we have some one explanation for that p. So retain that. I'll give later. And now we have to take that ap into z minus 1 to other side, and here p is common, take it outside. So p into 1 plus a square p square minus, here when you taking ap z to other side it becomes minus ap z and p is taken outside, so minus a z. Here also minus ap, when you taking this to left hand side it becomes plus ap and p is taken outside, so you have plus a alone is there, is equal to 0. Now from this, product of two terms is equal to 0 implies at least one term should be equal to 0 or both the terms are equal to 0. Here in our problem, p is not equal to 0 and only possibility is this is equal to 0. I'll give the explanation after finding the value of p. Okay, now we have to find out the value of p. A square p square is equal to, we have to take remaining terms to other side, minus az. When you taking to right hand side it becomes plus az and plus a becomes minus a, plus 1 becomes minus 1, or otherwise you have p square is equal to az minus a minus 1 divided by this a square, or p is equal to taking square root az minus 1 root of az minus 1 divided by a. This is the value of p. Now suppose if p is equal to 0, what happened? Then q is also equal to 0. What about dz? Then that is p0 q0, dz is equal to 0. Then integrating this, z is equal to constant, which is a complete integral or not? No, it is not the complete integral because a complete integral consists of two arbitrary constants. Here we have a single arbitrary constant. That's why this z is equal to c is not the complete integral and p is not equal to 0. For that reason only I ask you to retain this p here itself. Okay. So we have to make use of this, that is we have to write like this p, because this complete integral always consists of two arbitrary constant. Z is having single arbitrary constant here, so p not equal to 0. This is the way we conclude. And so here we have to get the value p here and substitute p and q values here. Dz is equal to dz is equal to pdx plus q is ap into dy. So integrating this, we have integral dz is equal to, p is taken outside, p into integral dx plus a dy plus a constant, and the value of p is substituted here. Okay, that is dz by p is equal to, here we have to take that p to denominator, so integral dz by p is equal to integral dx plus a dy plus a constant of integration, and where p is equal to root of az minus a minus 1 divided by a. That is substituted here. When you substituting this, here a goes to numerator because a is root of az minus a minus 1 divided by a, we are substituting, a goes to the numerator. So a dz by root of az minus a minus 1, which is equal to integral dx plus a dy plus a constant. Now that is, this constant is constant of integration. You have to integrate this. What is integration of this term? This is replaced by that is we have to apply integral of dx by root x. So integral of dx by root x is x power half, we can x power minus half we can write it. Okay, when you taking root x can be written as x power half. When you taking to the numerator it becomes x power minus half. What is the form differential integration formula? X power n dx, x power n plus 1 by n plus 1. So x power minus half is there, so we have to write like this, x power minus half plus 1 divided by minus half plus 1. That is x power minus half plus 1 is x power half, that is root x, and here you have minus half plus 1 is 1 by 2. So the 2 goes to numerator, so it becomes 2 root x. In the same way we have to apply this term. This is of the form that is ax minus a minus 1 whole power minus half plus 1 divided by minus half plus 1 into differentiation of this with respect to a. You have to write it in the denominator into a, and 1a is in the numerator, which is equal to integration of dx is x plus a into integral dy is y plus this constant. Now this a get cancelled, and the remaining terms you have is az minus a minus 1 whole power half, that is minus half plus 1 is half minus half divided by half, which is equal to x plus ay plus c, or you have 2 into root of az minus 1 minus a 2 into root of az minus a minus 1 is equal to x plus ay plus c, which is our required complete integral. Number that equation as 2. Now we have to find out the singular integral using this complete integral, that is differentiating this partially with the same rule you have to follow, differentiating this with respect to a and c, and using the rule dou z by dou a is equal to 0 and dou z by dou c is equal to 0, eliminating a between a and c between this, we can get the singular integral. So we have to differentiate this with respect to c partially, because c is separately there. So we had 0 is equal to 1 result, we got it as usual like the previous problem. We get 0 is equal to 1, which is an impossible result. So we conclude that there is no singular integral for the given problem. Now we have to find out the general integral for this. General integral is obtained from the singular integral. General integral is obtained from the complete integral. We have to substitute c is equal to phi of a in equation 2. This is our equation 2. Here we have to substitute c is equal to phi of a. Substituting 2 into root of az minus a minus 1 is equal to x plus ay plus phi of a, and then you have to differentiate, that is the number that equation as 3. Okay, that is a in the 2 into root of a is taken outside, z minus 1 is equal to x plus ay plus phi of a, that is differentiating this with respect to a. Then here we have to use the differentiation d by dx of root ax. What is differentiation of d by dx of that is root ax, which is 1 by 2 root ax into a, because a is there, so you have to write like this. So this formula is applied here. So 2 into root of a into z minus 1 minus 1 into this. Here in the place of a you have z minus 1, so you write like this, z minus 1 into this 2 you have is equal to, here differentiation of x with respect to a becomes 0, and differentiation of ay with respect to a is y, plus differentiation of phi of a with respect to a is phi dash of a. Number that equation as 4. Now this 2 get cancelled, and then eliminating this a between 3 and 4, we can get the general integral for this problem, because further we can't simplify this function phi of a is not known to us. That's why we conclude our problem like this. Okay, that's all for this video. If you have any doubts in this, please provide in the comment section. Thanks for watching and thanks for your time. Please be updated in the channel Alpha Numeric Tricks to get more videos. Thank you.